Hello, in this video I'll be working through Unit 1 homework problems 1 through 3. You may want to download a copy of the Unit 1 packet to follow along with the video. Question 1 says, a bungee jumper dives from a tower at time t equals 0. Her height h in feet at time t in seconds is given by the graph. In this problem we can base our answers on estimates from the graph, or we can use the equation for the jumper's height given by s of t. So on the graph, our horizontal axis represents the time t, and that is in seconds. And the vertical axis is the height of the jumper, and that is measured in feet. Part A asks, what is the change in vertical position of the bungee jumper between t equals 0 and t equals 15? So we want to find s of 15 minus s of 0. That's the final position minus the initial position. Using the graph, s of 15 is this point here, so we can follow that across to a height of about 100. Minus s of 0 is represented by this point on the graph here, so that height is 200. 100 minus 200 is negative 100. So overall, that change in position of the jumper is 100 feet. Part B, estimate the jumper's average velocity on each of the following time intervals, 0 to 15, 0 to 2, 1 to 6, and 8 to 10. Include units on your answers. So we want the average velocity of the jumper on the time interval 0 to 15. The average velocity is going to be the change in position, so s of 15 minus s of 0 over the change in time. Change in position over change in time. We've already computed s of 15 minus s of 0. We know that's negative 100. And the change in time is 15. So the average velocity, if we simplify that, is negative 20 over 3. And in the numerator, the change in position is feet. In the denominator, the change in time is seconds. So our answer is negative 20 feet per second. Next, we want to find the average velocity on the time interval from 0 to 2. So again, that's change in position, s of 2 minus s of 0 over the change in time, 2 minus 0. S of 2, if I use the graph, is 100. S of 0 we know is 200 over the change in time. So that simplifies to negative 50 feet per second. Next, we want the average velocity on the time interval from 1 to 6. Again, we want change in position, s of 6 minus s of 1, over change in time, 6 minus 1. S of 6, using my graph, looks like 90. Minus s of 1 looks like 150 over change in time. So that gives me negative 12 feet per second. And finally, the average velocity on the interval from 8 to 10. S of 10 minus s of 8 over the change in time, 10 minus 8. S of 10, I'm using my graph to estimate that. It's like 100. S of 8 looks like 120 over the change in time, 2. Negative 20 over 2 is negative 10 feet per second. Part C, on what time intervals do you think the bungee jumper achieves her greatest average velocity? Well, that would be where the graph appears to be the steepest. So that looks like it's happening right around here somewhere. So I'm going to say between t equals 1 and t equals 2. Because the graph is the steepest. Part D. Estimate the jumper's instantaneous velocity at t equals 5. So not average velocity, but instantaneous velocity. Now the instantaneous velocity is going to be approximately equal to the average velocity on a very small interval. So we want to estimate instantaneous velocity at t equals 5 seconds. I want a really small interval surrounding 5. I could try maybe 4.999 to 5.001. That's one option. And I have an equation that would be very difficult to do on the graph. But since I have the equation, I could compute that value. Or I can go from 5 to just a little bit more than 5, maybe 5.0001. Or in general, I'm going to say 5 plus h, where h is a small value. So the smaller h, the better my approximation is for my instantaneous velocity. So let's go ahead and find an expression for the average velocity on the interval from 5 to 5 plus h. And we'll do that the same way we did a moment ago. We're going to find the change in position, so that would be s of 5 plus h minus s of 5 over the change in time, 5 plus h minus 5. And we can simplify that. S of 5 plus h minus S of 5. Now, S of 5, we can estimate from our graph. Looks like it's 70. So I'll go ahead and say 70 over, and then 5 plus h minus 5 is just h. So there's my equation for average velocity in terms of h. And as long as I use a really small value for h, I'm going to get a good approximation for instantaneous velocity. So we're going to let h equal 0.01. So really, we're finding the average velocity on the interval from 5 to 5.01. But since that's such a short interval of time, it'll give us an approximation of instantaneous velocity. So instantaneous velocity at t equals 5 is approximately equal to s of, now 5 plus 0.01 is just 5.01, minus s of 5, which I said was 70, but since I'm going to use the equation, I'm going to recalculate s of 5, try and get a more accurate approximation, over h, so over 0.01. And using my calculator, if we round to 3 places, I'm getting 70.032 minus 69.813 over 0.01, which gives 21.854 feet per second. And if I had chosen an even smaller value for h, I would have gotten an even better approximation. Then part E, among the average and instantaneous velocities you computed in earlier questions, which are positive, which are negative? What does negative velocity indicate? The only positive value we computed was for this instantaneous velocity at t equals 5. All of our average velocities that we computed in part B were negative. And that's because the change in position was negative. So I'll say negative velocity indicates a decreasing position. Now for number 2, we are asked to sketch a graph of a diver's height as he leaps from a springboard and enters a swimming pool. So we're given the following information. A diver leaps from a 3-meter springboard. So at time t equals 0, I know the diver's height is 3. Let me go ahead and label my vertical axis here, 1, 2, and 3, and that will be in meters. So at time 0, his height is 3 meters. His feet leave the board at time t equals 0. He reaches his maximum height of 4.5 meters at t equals 1.1 seconds. So 4.5 meters, it's a little bit off of our graph paper here, but that's okay. And he enters the water at t equals 2.45 seconds. So a little bit less than 2.5 seconds. He enters the water, meaning his height above the water is 0. Once in the water, the diver coasts to the bottom of the pool, a depth of 3.5 meters. Touches bottom at t equals 7. So at t equals 7, his height is negative 3.5. Rests for 1 second, so he'll have a constant height during that 1 second. And then pushes off the bottom. From there, he coasts to the surface and takes his first breath at t equals 13. Okay, so let's sketch what this might look like. Okay, starting at t equals 0, and then he leaps from the springboard, so his height is increasing. He reaches his maximum height, and then he starts decreasing. We have our x-intercept here at 2.45, and he's then coasting along to the bottom, levels off for that 1 second, and then he pushes off. So he's going to be increasing quickly but slowing down as he approaches that surface there. So that was part A, to sketch that graph. Part B asks us, what is the average velocity of the diver between t equals 2.45 and t equals 7? So the average velocity on that time interval, 2.45 to 7, is going to be the change in position, so s of 7 minus s of 2.45 over the change in time, 7 minus 2.45. S of 7 is negative 3.5 minus s of 2.45 is 0 over 7 minus 2.45. And that simplifies to negative 0.769, and our units there are meters per second. The change in position is meters, the change in time is seconds, so meters per second. The second part of that question says, is his average velocity the same on every interval within the interval 2.45 to 7? Well, no, it wouldn't be, since his speed is not constant in the water. Part C asks us to sketch a graph to represent the diver's instantaneous vertical velocity. Let's start by thinking about when his instantaneous velocity would be 0. So that means when he's at rest. Well, when t equals 0, he's at rest. And when he reaches his maximum height, just for a moment, he's at rest. So that happens at 1.1. So put that right about there. And then between 7 and 8 seconds, he is also at rest. So between 7 and 8 there. Now between time t equals 1.1 and time t equals 7, His height is decreasing, so we know his instantaneous velocity should be negative. From 0 to 1.1, his height is increasing, so our graph should be positive between 0 and 1.1, then negative from 1.1 to 7, and positive from 8 to 13. So let's just see what we get. Now, I'm not real sure about the height here unless I start actually computing some average velocities to get a better idea, but it's okay. We're just going to do a rough sketch here. Something about like that. For number 3, we're given some population data. According to the U.S. Census, the population of the city of Grand Rapids, Michigan was 181,843 in 1980. So let's just make a 2-column chart here. Year 1980. And population was 181,843. In 1990, the population was 189,126. And in the year 2000, the population was 197,800. Part A asks, between 1980 and 2000, by how many people did the population of Grand Rapids grow? So between 1980 and 2000, by how many people? We just need to subtract those populations. And that gives us 15,957 people. Part B, in an average year between 1980 and 2000, by how many people did the population of Grand Rapids grow? So the total amount of growth between 1980 and 2000 is 15,957 people, but that is a change over 20 years. So to get the average per year, we would want to divide that by 20. And that gives us 797.85, or approximately 798 people per year. Part C, what does f of b minus f of a over b minus a, what does that measure on the graph of y equals f of x over the interval from a to b? Well, that's the calculation that we just computed in part B. So that is giving us the average change in population per year. Gives the average rate of change of the population per year. Part D. Let P of t represent the population of Grand Rapids at time t, where t is measured in years from January 1st, 1980. What is the average rate of change of P on the interval from t equals 0 to t equal 20? What are the units on this quantity? We've actually already computed this. From t equals 0 to t equals 20 would be from January 1st, 1980 to January 1st in the year 2000. So that average rate of change is 797.85 people per year. Part E, if we assume the population of Grand Rapids is growing at a rate approximately 4% per decade, we can model the population function with the following formula. P of t equals 181,843 times 1.04 to the power t over 10. Use this formula to find the average rate of change of the population on the intervals 5 to 10, 5 to 9, 5 to 8, 5 to 7, and 5 to 6. So we want average rate of change on the interval from 5 to 10. And 5 to 10 represents 1985 to 1990. So we want the population when t is 10, so p of 10, minus the population when t is 5, minus p of 5, over the change in the number of years, so 10 minus 5. Now hopefully this looks familiar. This is how we were finding average velocity in the previous problem. So average rate of change is a similar calculation to average velocity. In fact, velocity is a rate of change. It's just the rate of change of position. So instead of calling something average velocity, we could call it an average rate of change. And we'll use our calculator by substituting 10 into our equation for p of t, substitute 5 into the equation for p of t, find the difference, and this should come out to be 734.504 people per year. The average rate of change on the interval from 5 to 9 would be p of 9 minus p of 5 over 9 minus 5. And again, using the equation and our calculator, we should get 733.061 people per year. Average rate of change on the interval from 5 to 8. P of 8 minus P of 5 over 8 minus 5. And that one is 731.621 people per year. And we'll compute the remaining two in a similar fashion. So average rate of change on the interval from 5 to 7, 730.185 people per year. And average rate of change on the interval from 5 to 6, 728.754 people per year. And finally, part F. How fast do you think the population of Grand Rapids was changing on January 1st, 1985? How fast was it changing on that day? So we want an instantaneous rate of change when t equals 5. 1985 corresponds to t equals 5. So to find the instantaneous rate of change, we're going to use our average rate of change formula, and this is going to give us an approximation. So if we use a very small time interval, we're going to get a pretty good approximation for instantaneous rate of change. So it's approximately equal to the average rate of change on the interval from, and we have a choice. We can take an interval on either side of 5, maybe 4.999 to 5.001. That's one thing we could do. I'm going to go from 4.999 to 5. So that would be, and again, I erased it, but we're using that equation for P of t. So P of 5 minus P of 4.999 over the change in time, 5 minus 4.999, which is approximately 727.324 people per year. How many additional people should the city have expected in the following year? Well, about 727 more people, because that's how much we've estimated are going to be added each year. At that moment in time, that's how fast the population is growing.